Hello, my name is Jihan Park. Today I'll be introducing the paper VGGT, Visual Geometry Grounded Transformer. The paper was accepted to CVPR 2025 and was given the Best Paper Award. Let me start with a quick background on what 3D scene reconstruction actually means. When we have a set of images, the goal of the field is to estimate all the underlying 3D information hidden inside them, things like camera poses, depth, and the 3D structure of the scene. Traditionally, this is done through geometry-based pipelines such as structure from motion, multi-view stereo, and bundle adjustment. These methods rely on handcrafted geometric optimization techniques and have remained the core approach for decades. Recently, learning-based methods have started supporting smaller parts of the pipeline like feature matching and depth prediction. However, even with machine learning helping certain steps, most state-of-the-art 3D reconstruction approaches still rely on iterative optimization while only being capable of processing one or two images at a time. In addition, these pipelines are fragmented, meaning that depth estimation methods don't provide estimates for the camera parameters. Because of these constraints, existing systems are slow to run, difficult to scale, and not unified across tasks. Today's paper, VGGT, proposes a very simple idea. Take a large transformer and train it end-to-end to directly output all 3D scene information in one go. The model takes anywhere from one image to hundreds of images as input. And in a single forward pass, it outputs camera extrinsics and intrinsics, depth maps, point maps, and per pixel features for 3D point tracking. The key idea is that a large model trained on a massive amount of 3D annotated data can learn to infer geometry implicitly without the need for traditional iterative optimization pipelines. The input to the model is a set of RGB images of a scene, and the output is a combination of 3D properties of the scene. The camera parameters is a concatenated vector of three attributes: rotation, quaternion, translation vector, and field of view. Depth map provides the depth values of each pixel in an image. Point maps represents the 3D point associated with each pixel that are defined in the coordinate system of the first camera. The final one is the C-dimensional vector used for key point tracking, which serve as an input to an external module. We now look at how the processes are done step by step. First, VGGT patchifies each image and extracts visual tokens using a dyno-based vision transformer. Then the model augments these tokens by adding 5 learnable tokens, 1 camera token and 4 register tokens. These tokens help the transformer organize information and provide dedicated slots where frame-level structure can be stored and exchanged during attention. Here, one thing to note is that there are actually 2 sets of token pairs, one set used only for the first frame and another shared by all other frames. This allows the network to reliably distinguish the first frame and to express all 3D outputs using the first frame's camera coordinate system. In other words, the first frame acts as a world coordinate anchor. The concatenated tokens then go through the core of the architecture, the alternating attention transformer. Instead of always applying global attention, VGGT alternates between 2 modes: global self-attention, which lets the model exchange information across all frames, and frame-wise attention, which focuses only within each individual image. By switching between these two, the model learns both detailed per-frame information and the global geometric relationships across views. After passing through the transformer, each frame's camera token is used to predict that frame's camera parameters. The register tokens are discarded at this point as they only act as temporary memory during processing. The camera head consists of 4 self-attention layers followed by a linear layer. This head predicts rotation, translation, and field of view parameters for each frame. The first camera is fixed to the identity pose, so all other cameras are expressed relative to this first frame. For dense outputs like depths and point maps, VGGT uses the decoder architecture of a dense prediction transformer. The output tokens from the transformer are converted into dense feature maps Fi and dense feature Ti. The dense feature maps Fi are used to produce depth maps and point maps. Depth maps and point maps also come with a confidence level, which allows the model to handle noise and uncertainty more robustly during training. Dense features Ti are fed into an external module CodeTracker2 for multi-frame point tracking. Here are some examples of the model's tracking results. You can see that the target points in 3D scenes are located and visualized across multiple views. With these outputs, the model is trained using the following loss functions. For the camera loss, the model adopts the Huber loss between the ground truth and the prediction. By applying a threshold that switches the loss from quadratic to linear for large errors, the Huber loss is capable of robustly handling outliers. For depth maps and point maps, the model uses an uncertainty-weighted L1 loss. For each pixel y, the model predicts both the depth and an uncertainty value written as sigma. If the model is confident, the sigma becomes small, so the pixel has a small influence in the loss. If the model is uncertain, sigma becomes large and that pixel is downweighted. This makes training much more stable, especially in noisy or occluded regions. For tracking, the model is trained to match 2D correspondences across all frames. Here, M is the number of target points we track across the images. The loss measures how accurately the model predicts where each point in one frame appears in all other frames. For evaluation, VGGT is trained using a very large and diverse set of datasets including Blend MVS, Megadepths, ScanNet, and so on. The datasets comprise of various scenes including indoor, outdoor, real, synthetic, scanned environments, and more. For camera pose estimation, the baselines are evaluated on Real Estate 10K and Co3DV2 using 10 randomly sampled frames. The metric used is AUC30, which measures how often the model predicts camera motion accurately up to a tolerance of 30 degrees. A higher score means more reliable and consistent pose estimation. The results show that VGGT achieves state-of-the-art performance while being significantly faster even without any post-processing. For depth evaluation, the baselines are tested on the DTU dataset. Here we look at both accuracy and completeness. Accuracy tells us how close the predicted points are to the ground truth surface, while completeness measures how much of the surface the model is able to reconstruct. The results show that VGGT achieves performance comparable to methods that use ground truth camera parameters, and it performs the best among the methods that do not rely on them. For point meta estimation, the baselines are evaluated on the ETH 3D benchmark. Here, two settings are reported. Hours point refers to the model's direct point map direct predictions, while hours depth plus cam reconstructs point maps by combining the predicted depth maps with the predicted camera poses. Although VGGT achieves the best performance among all baselines, the depth plus cam setting performs even better than the direct point map head. This highlights the benefit of decomposing the complex task of point map estimation into simpler subproblems of predicting depths in cameras, despite the fact that camera poses, depth maps, and point maps are jointly supervised during training. These qualitative examples show the quality of VGGT's 3D point predictions. The model produces clean, detailed point clouds and accurately captures fine structures across a variety of scenes. The baselines are also evaluated on image matching using the ScanNet dataset. Image matching measures how well the model finds corresponding points between different images. Even though VGGT was not explicitly trained as a feature matcher, it outperforms specialized matching methods, demonstrating that it learns very strong geometric features. The authors have conducted an ablation study to verify the effectiveness of the alternating attention design. By comparing between backbone variations, we see that the alternating global attention with frame-wise attention produces the best performance. The next ablation evaluates the impact of multitask learning. Training the model simultaneously on camera pose, depths, point maps, and tracking results in significantly better point map accuracy than training any of the tasks individually. This shows that the tasks reinforce each other and help the model build a consistent 3D understanding of a scene. Finally, the model does have some limitations. It does not currently support fisheye or paranomic inputs, and its performance drops under extreme rotations. It also struggles in scenes with large non-rigid motion. However, the authors emphasize that these limitations mostly come from the training dataset and can be resolved by using datasets that better cover these cases without requiring changes to the model's architecture. Thank you.